So enthalpy is given with the variable H, because why wouldn't it be? Okay. All of our most of our variables, I feel like this chapter don't really relate, but enthalpy is given with an H. It's a kind of an abstract concept, but essentially what enthalpy is a thermodynamic equivalent to the total heat of the system, right? The total heat of the system, including the internal energy of it, plus the pressure and the volume, right? All of those things add to the heat. If we've got increased pressure, things start moving quickly. If we've got decreased volume, things start moving quickly, which increase the heat. Okay, it doesn't necessarily change the energy, but it changes the heat. Okay, so as we start looking at enthalpy, this will be kind of a big topic here in this chapter. We'll deal with enthalpy qualities and the change in enthalpy of reactions. I hate to say it, but the definition of it it's not super crucial to us being able to solve the problem. So if the definition still seems a little abstract, that's okay. But we're going to have lots of looks at, in a chemical reaction, what is the enthalpy change, right? Where is the heat changing? What's happening with it? So enthalpy is given with the H. It's energy plus pressure and volume. Did I put those equations on there for you, or did you get those down? Okay. The change in enthalpy, or the change in the total heat of the system, is also equal to our Q that we learned yesterday, right? The Q variable stands for heat. So when we talk about change in enthalpy, we're really talking about heat as well. When we talk about change, it's always the change in final minus initial. And we're going to be looking at the change of enthalpy in a chemical reaction. So it's really going to be the change of enthalpy of the products minus the reactants. Final minus initial. So we'll see that here in just a little bit in some examples, but we're going to take the enthalpy final, or the enthalpy of the products minus the reactants. And then I gave you the endothermic, exothermic for both of these. But it should be pretty self-explanatory, right? If our change in heat is positive, that makes sense that it's endothermic. If our change in heat is negative, that makes sense that it's exothermic. Heat's flowing out of that. All right. Did I skip forward 2 minutes? Is that your next slide? Yeah. Okay. All right. We're going to try one here. Practicing with an enthalpy equation. There we go. No. Consider the combustion of propane. This says that the change in enthalpy of this whole reaction, okay, and that's what we're going to look at. They're going to give you a reaction, and they're going to tell you what's the total change in enthalpy for the reaction. So they do a lot of the work for you. But it says when this reaction takes place, there's a change in enthalpy of 2,221 kilojoules of released heat. Agreed? Okay? That's how much heat is released if we start with 1 mole of propane. Right? Since this is our mole ratio, 1 mole of propane releases that much. But the question we're trying to answer is, calculate the delta H in which 5 grams of propane is burned. So instead of doing a whole mole of it, we have to see how much heat will be released if we only use 5 grams of propane instead of a mole of propane. Okay? So are the wheels turning as to how you could start solving that problem? Okay? Let's first look at, well, how many moles is 5 grams of propane, right? That's the first goal. So let's go ahead and do that. We need to see what's the 5 grams of C3H8, and we're going to convert that to moles. Okay, grams of propane, C3H8 to moles, C3H8. Grab your calculator out if you don't have that out just yet. 44 grams. So I'm going to take 5 divided by... I actually can't do that one in my head, so... Okay. That gives us 0.1136 moles of C3H8 that were used. So if I know that one mole of our propane produces this much heat change, I could just do another conversion to say, well, how much would 0.1136 moles produce? Yeah, I would go 0.1136 moles, and I'd say 1 mole is negative 2.221 kilojoules, right? You could even do that in a continuation of the T-chart if you wanted. You could have kept going and saying 1 mole was 2.221, whatever the kilojoules was. So you're multiplying it. Not dividing, you're multiplying. Okay, which means I came out at negative 252 kilojoules of heat that was, well, I guess I should say lost or escaped rather than produced. Okay, and because it's negative, that means the heat is flowing out of the system.
Why is it negative?
Well, it told us that in the original scenario, in this reaction, it's going to release heat. So we're still having the same reaction, we're just using less of our reactant. Okay? That's going to be the case a lot of times. When we said that delta H is products minus reactants, we're very rarely going to have to do that math. It's going to give us the enthalpy change for the reaction, and then we're going to be able to manipulate that to see what's actually going to happen in a scenario just like this. Okay? But it'd be rare that we'd have to do the products minus reactants subtraction. Any questions about that one? Now let's move into, I think, calorimetry. Is that your next slide? Or was there one more? Okay, I don't know why I'm not able to move through this smoothly. There we go. All right, when 1 mole of CH4 is burned at constant pressure, 890 kilojoules is released. Calculate delta H for a process in which 5.8 grams of methane is burned. So this is a very similar question, except you don't even have to have the balanced reaction. Right? It says when 1 mole of it is burned, we release this much energy, but instead we want 5.8 grams. So I want you to go ahead and solve this one. It's very similar to the one we did. Why do you think released is in red italicized?
Because it's important.
Right. It determines whether this is negative or positive. Okay? So you have to make that determination and then do it correctly. Each part of a chemical reaction has what's called a specific heat capacity. Specific heat capacity. And all it is the energy that it takes to raise that object 1 degree Celsius. Right? All it takes is to get, it's how much energy it takes to raise that 1 degree for 1 gram of the substance. And each individual substance has a different specific heat capacity. Water has a different specific heat capacity than ethanol, than iron, than whatever. Do you think metals have a higher or lower specific heat capacity than water? So think about what it means. Specific heat capacity means how much energy does it take to make it hot or cold? Do metals have a higher or lower specific heat capacity than water?
Higher.
Because it takes longer for it to heat up.
You guys can't decide what I think. It's lower. It's lower. Because when I want to heat water on my stove, what do I put it in? A metal pot on a metal grate, right? Those things get hot way faster than water does, right? Water has a really actually very high specific heat capacity. It's like 4.18. Most metals are under 1. Okay, so the amount of energy it takes to heat water by 1 degree Celsius, it takes a lot more heat than it takes to move metals temperature. hotter or colder, right? Metal has a very low heat capacity, specific heat capacity, because it does conduct heat really well, right? That's the point about metals, is that heat moves through it very quickly and very easily. So very low specific heat capacity. All right, molar heat capacity is very similar, except it's the amount of energy required to raise the whole mole of the substance by 1 degree. So it's got a different scale. Not something that we'll use very often. We'll use specific heat capacity more often because we want to deal with things in their mass, not in moles. Okay, so. All right. Calorimetry. If two reactants at the same temperature are mixed, and this resulting solution gets warmer, that means the reaction is exothermic. It's releasing heat into the environment. And if it's endothermic, that means that it's actually getting colder. Okay. Here's coffee cup calorimeter. I already showed you that.
Why are there 2 styrofoam cups?
One of them acts as the actual holder. The second one acts as the insulator. All right, something actually has to hold the liquid, and then the second one acts as an insulator. Yeah. Okay. All right, so here is our major equation that we're going to use for this chapter and this part of the unit. Q equals ms delta T. M is the mass in grams, not kilograms. S is specific heat capacity, and delta T is change in temperature. The units have to match. Okay, we have grams, degrees Celsius, joules is going to be what our heat is measured. Okay, so if you want to write this down, you can. If you want a separate equation sheet, we can do that too. But I would make sure you have that equation highlighted, circled, something. This is one that we'll use most often. Okay, this also, I want you to point out, this equation is just for one substance. If we were looking at what happens in a change, we would say the heat lost by one is equal to the heat gained by another, and we kind of combine those two things, and we'll see that in a little bit. Okay, but this is just one substance. What's the heat in that substance at that time? Okay, this next one is molar heat capacity. I don't use this one as much, but I put it on there in case we needed it. But the same thing is true here. It's moles of a substance, then molar heat capacity. I should have put molar there. And then change in temperature. Okay. Not going to use that one as often, but it can be used. Okay, let's try some. How much energy or heat is required to change the temperature of 50 grams of water by 15 degrees Celsius? I would highlight this. The specific heat capacity of water is 4.18. That's not going to be given to you in most problems. You'll have to know that one. Okay, so the S value for water is 4.18. So I'd highlight that maybe. If you have an equation sheet, put it on your equation sheet, because that's not one that's going to usually be given to you in most problems. All right, how much energy? So we're looking for Q equals ms delta T. Q is what we're solving for, so we're going to leave that. Our mass is 50. It gets to stay in grams. 4.18. And then do we have an initial and a final temperature? Do we have a final and initial? No, but we don't have to because they gave us the change, right? We don't need to know what it started at and what it ended at because they told us the delta was 15. So we just plug in 15 as that delta T.
Is S constant?
Nope, it's different for each material.
Each material.
Right. So sometimes it'll tell you the specific heat of this reaction or of this mixture is this, right? But it is material specific. So on this one, did we get about 3,135 joules? Okay, good. Okay, that's all that we're saying here is in order for this water to change by 15 degrees, and we assume positive 15 degrees, right? Because it went up. It didn't say cooled by 15 degrees. We're going to put in this many joules of heat. Okay. Questions about how that gets plugged in? Okay. What's the final temperature after 840 joules is absorbed by 10 grams of water at 25 degrees Celsius? Okay, so this time we're looking for final temperature. The 840 joules, what variable does that go with?
Q.
That's Q. Here's my mass. And what is this value?
Initial.
Yeah, TI, or initial temperature. Okay, we didn't give you the S value, but you know that it's 4.18. So 840 equals 10 times 4.18 times, is it 25 minus TF?
T minus 25.
Yeah, TF minus 25 because it's temperature final minus temperature initial. So this would be 41.8 times TF minus 1045 equals 840. Does everyone understand? We good on the distributing that through? Right, I just distributed that. 10 times 4.18 is 41.8, so times TF, and then times negative 25. I'm going to add that to the other side.
Do we have to distribute? Because I just divided it by 41.8 and then added 25.
Sure. Yeah, I would think that would work. Did you get 45.1?
Yeah.
Okay, great.
No, I got 45.487.
Okay. Is our final temperature reasonable? Right? Is our final temperature reasonable? What if we had gotten a final temperature of like 10,000 degrees? Is that reasonable? Right? If we had gotten a final temperature of 6 degrees, that wouldn't be reasonable because we put in heat. Right? So I want you to make sure that as you're going through these things, you're checking to make sure, does my answer really make sense? Right? And if it doesn't, then we need to adjust something, but it's good. All right, now let's try adding two substances together. So now we're going to have some mixtures. We're going to have some different things that we have to pay attention to. This says 12 grams of NaOH is added to 50 grams of water. The temperature rises from 25 to 29. Specific heat of the solution is 3.9. What's the heat of the solution? Okay. So in this scenario, the only thing that we have to change, since they gave us the specific heat of the solution, not of the specific heat of the individual NaOH and water, we're going to be able to just solve the same thing, except the mass has to just be the masses added together. That's it. Okay, if it would have given us specific heat of NaOH and specific heat of water, we would have solved it a little differently. But since it tells us the specific heat of the total solution is 3.9, we're going to say 50 plus 12 times 3.9, and then final minus initial. Okay, that's it. So you need to pay attention to if it tells us, is this the specific heat of the solution, or is this the specific heat of individual substances? Because it does make a difference. Let's see. 62 times 4. 967.2 joules. Okay. And we raised our temperature, which means we should come out positive here. If our temperature had been lowered, it would have automatically come out negative because my delta T would have been negative. Right? So it should come out in the correct direction for you, the correct sign.
So if it was like giving us the
All right, here we go. We have a styrofoam cup with 50 grams of water at 10. You add a 50-gram iron ball at 90. Calculate the final temperature of the water. This is literally exactly what we're going to be doing in the lab. Okay, this is the type of scenario we're going to be talking about. So we've got a cup of cold water. We've got something hot that we put into it. And we want to see where are those going to come to equilibrium at. What's the final temperature of that water going to be? We need to take just a second here and think, well, what's the range of that temperature? What's it going to fall between?
Okay.
10 and 90, right? The water is not going to be colder than when it started, And the iron is not going to make the whole solution hotter than what the iron started at, right? We've got a range there that we're looking. That was just something I wanted to point out so we don't get like crazy ahead of ourselves here. Okay, so when we solve these problems, there's a really important kind of concept that you need to understand. Which one of our objects is going to be losing energy, the iron or the water? The iron's going to lose energy to the water, right? Iron's hot, water's cold. When we put them together, some of that heat will flow from the iron into the water to warm it up. Agreed? So we want to say the heat lost by one object has to be equal to the heat gained by another. Does that statement make sense? That's the law of conservation of energy, right? If one loses, the other one has to gain. How we're going to solve these problems, where we've got two scenarios. The thing that we have to pay attention to is we have to add the negative there on one of the sides, most likely the side that lost heat. Okay? Whatever one let energy flow out, the other one flowed in. So we've got to have a negative on one side. So that's just something I wanted to point out. And so the way we'll solve these is we'll just say negative ms delta t is equal to ms delta t of the other substance. Okay, that's going to be a formula that we use a lot. So if that one or this one you want to write down on your equation sheet or circle it or something, we're going to use this a lot when we have two scenarios coming together. All right, so I'm going to set this problem up exactly like I just had it at the top of the, oh, wow, okay. I didn't realize I even put it there. Okay. We can set it up just like this one, that's fine. Which one of my objects was gaining heat? Iron or water? Water. So let's go ahead and just keep water on the left side like this equation right here. The mass of the water is 50. The specific heat of the water is 4.18. And the final temperature we don't know. We do know the initial temperature was 10. Okay? All of that heat from the water has to be equal to the amount of heat lost by the iron. So I'm going to make sure I add the negative. The mass of the iron is 50. The specific heat of the iron is 0.45. And then the final temperature, we don't know. Right? But we know it started at 90. Okay? Are we understanding that the final temperature of these two objects are going to be the same, right? It's going to come to equilibrium so that the metal and the water are going to have the same temp. Okay? So if it were me, I'm going to distribute that through. You guys might solve it in a different way. So I'm going to have 209 TF. Okay, that's how I do the algebra. If something else works better for you, you guys know how to do that, so that's fine. Now I'm going to combine like terms. I had 17.8 degrees Celsius. Is that about what we had? Okay, now think about this. Is that answer seem reasonable? First of all, it fits within our range. That's good. Second of all, we know that the metal is much more easily influenced by temperature than water, right? So it should make sense to us that our scale is leaning toward water's original temperature. Agreed? It takes a lot more energy to move the temp of the water than the temp of the metal. So the metal is more easily I'm going to acclimate to that new environment.